All right, good morning, everyone, and welcome to the JKMRC Friday seminar series. On behalf of the University of Queensland and the Sustainable Minerals Institute, we would like to acknowledge the traditional owners and custodians of the land on which we meet today. We pay our respect to the ancestors and their descendants who continue cultural and spiritual connections with country. And we recognize their valuable contributions to Australia and the global society. It's my great pleasure to welcome Dr. Julie Pearce today. Julie has international experience in the UK, Japan, and Australia in interdisciplinary projects and is currently an ARC Mid-Career Industry Fellow at the University of Queensland Gas and Energy Transition Research Centre and School of the Environment. She's an expert on gas-water-rock interactions with a focus on CO2 geological storage. She's also working on field-based techniques for measurements of dissolved gases and understanding potential methane leakage processes and interaquifer connectivity through geochemical and isotopic techniques. Julie is collaborating in research projects with the gas and CO2 storage industries and has provided expert opinions to the government. Today, her talk is going to be about CO2 water rock impacts to groundwater during CO2 geological storage with impurity gases. Please join me to welcome Julie.
I think actually this one's not working. So can you hear me on that one? Yeah. All right, thank you everyone for coming. So I'm going to talk about what happened, partly looking at a project that we were doing in Queensland that came into the media quite a lot in the regional media last year. You may or may not have heard about it. So this was a project that was with CTSCO, who are part of Glencore, that were looking at injecting CO2 in the Surat Basin. And at UQ, we were doing a lot of different research around looking at different gas-water-rock reactions, potential impacts to the groundwater, and also some of the field studies. I'll talk a little bit through some of those today. So let's see. So for those of you who are not that familiar with CO2 storage, am I not in the camera? Thanks. For those of you not too familiar with CO2 geological storage, this usually, it would usually involve the injection of a captured CO2 stream into a suitable reservoir underground. So a CO2 stream could be from various different sources, power plants, for example. Also recently in some countries, they're looking at direct air capture, where you're just sucking CO2 out of the air and then injecting it. There's various different kinds of reservoirs that people are looking at. So I'll be talking about sandstone reservoirs, where we have a sandstone reservoir and mudstone cap rocks or seals. There's all sorts of other different ones. You can have depleted reservoirs. Some people are looking at basalts or ultramafics as a possible reservoir as well. So in the case I'll be talking about, we were looking at a reservoir that was between 1 to 2 kilometres deep. And then you're going to have a seal or a cap rock that structurally sits over the top to prevent CO2 migration out of the system. So when you have a lot of these environmental impact assessments, or before that, the kind of site appraisals, you're going to be quite site specific because the geology can be a very important factor. And traditionally, you usually end up looking at things like deep saline aquifer injection. But in Australia, there were a couple of sort of more low salinity reservoirs, sandstone reservoirs, that were proposed as good reservoirs for storage. but because they're a low salinity, they had other uses in other areas. And also, I guess some of this work is applicable if people have overlying aquifers over the reservoir where there might be some concern that you might possibly get CO2 leakage out, although that's very unlikely. So it's important generally to understand potential impacts to some of the rock properties, some of the water resources, and if some of these different impacts are going to stay in the expected areas. So if you've got injected CO2 and it sits as a plume and it's interacting, that it's staying where you think it's going to stay. I'm going to talk mostly about rock reactivity and a bit of water impacts. I'll briefly talk about one of our projects on groundwater, but not for very long. So this is the Surat Basin. I'll try and use this one so that the people on Zoom can see. So basically going out west. So this is the town of Miles, for example, out here, and Romer's out over here. So this is the Surat Basin where there was a demonstration scale CO2 injection trial proposed by CTS Sky, part of Glencore, for the feasibility of geological storage. So initially we were looking in this area near the town of Wandoan, and there was a well drilled up here for feasibility studies, what we call the West Wandoan 1 well. For various reasons, a proposed demonstration scale injection didn't happen up here. And then we were looking further south here, where this red star is roughly, down in the West Wandoan area where there was there were two wells drilled. There was one well drilled for the proposed injection, another one close by for monitoring, and then there were several different monitoring wells, another 4 monitoring wells drilled around the area. That was separate to the Mooney oil field, if any of you have come across that. So the Mooney oil field, they were also around the same time looking at doing CO2 injection for enhanced oil recovery. And both of those were looking at getting their CO2 source from the Millmerran power station at the time. So roughly when you're injecting CO2 underground, it's going to dissolve in the formation water and you get some acidification of the groundwater, which induces different rock reactions. When you're looking at some of these industrial captured CO2 streams, they can contain other gases. So in low concentrations, but well, you'll have some what we'd call inert or non-reactive gases that are present. And we've also got some others that we might want to call reactive gases. So SOx and OX, sometimes oxygen, depending where you're getting your CO2 stream from. And some of those can have a bit of a higher acidification, or if you've got oxygen there, you're going to have other impacts going on underground. And if you end up looking at a storage hub, so in some places people are looking at taking CO2 from various sources and as a hub and then injecting it underground, you might have a mixture of compositions. So sometime last year, the Farmers Federation went into the news, especially in some of the regional news, that they were opposing the Glencore's carbon capture trial because the reservoir is part of the Great Artesian Basin. So this just kind of gives a illustratory cross-section, if you like. So I've taken this one from Ogier. So the Precipice Sandstone is down here in a pale, sort of a blue colour. So that's the reservoir that we're looking at. And then overlying there's the Evergreen Formation with a seal. And then the Hutton Sandstone aquifer overlies that. Here, this is the this brown area here is the Walloon coal measures. So in sort of further areas up north, this is where we're extracting coal seam gas. And then there are various other aquifers here that are used as part of the Great Artesian Basin. So as you probably know, aquifers of the Great Artesian Basin have a lot of different users. You get water abstraction from some of the mines. Agriculture's a big one. Some of the feedlots around taking water from various different aquifers. Town water supplies, so Gundawindi, Miles Town water taking from various different aquifers. So when you're going out west, obviously, as many of you probably know, in some of these regional places, groundwater's a big, important resource. So there's also cultural significance of the waters from the Great Artesian Basin and some of the Great Artesian Basin springs. Although these springs are many hundreds of kilometres away from where we were talking about, it still became part of the rhetoric, I guess, that was going on in the media. And just to say what else is going on around, I guess there's obviously coal seam gas and produced water from the coal measures. And then there's also other things like gas extraction from the Bowen Basin that sits underneath the Surat, and there's the Mooney oil field nearby extracting oil. So there's lots of things going on, which you might be well aware of. That's to give you a strat column. So again, I'll try and use this one. So the Precipice Sandstone's down here. Then we have the Evergreen Formations, the Seal. The Hutton Sandstone is one of the aquifers. And then there's a wall in coal measures and some of these like the Gubramunda Sandstone, the Muga Sandstone. And the Precipice Sandstone itself, which was our reservoir in other areas, is a well-used aquifer as well. So just to give you an idea of some of the scale, because this was talking about just doing a pilot injection. So it was a small scale injection. So again, this is a map of the Surat Basin, but this area here, I'm not sure if you can see there's probably, yeah, you can't really see the scale bar very well, but this is the West Mooney 1 injection well here. And these are the predicted extent of the plume. So when you're injecting supercritical CO2, it tends to move into the strata of the rock and then sit in quite a static area. And this is around 1.6 kilometres across here. So you can see they're blown up different predictions of the plume extent. So we're talking like less than 2 kilometres distance here. But when we were looking at what was going on in the media, we started having discussions about the Blackhall Bore, which takes groundwater from the Great Artesian Basin, which is hundreds of kilometres away from what we were actually talking about, which is down here. There was a lot of discussion about whether these were confined aquifers or unconfined aquifers, even though, again, the scales involved for hundreds of kilometres. And then last year, just unfortunately around the time when we had a state election, the Queensland government rejected the environmental impact, the EIS, for the project. And then very quickly, they went on to then, and that was one thing that could have been contested, but then they went on and very quickly put a ban on doing CCS in anywhere where the Great Artesian Basin exists. So this blue line here is showing the extent of the Great Artesian Basin. So here's Queensland here. As you can see, most of Queensland is under part of the Great Artesian Basin. It goes into New South Wales down here, into South Australia. So you may have heard of the Santos's Moomba site where they're doing CCS, and that's here within the extent of the Great Artesian Basin. So AgForce tried to push the legislation out into other states, but they rejected that. And I'm just going to show this one because I thought it was interesting. A lot of the times in the media you would see this image of the Great Artesian Basin, which kind of makes it look like one great big sort of underground lake. And although a lot of the regional landholders are very knowledgeable about what's going on, there are some people, I guess, who do still have this concept that the Great Artesian Basin is one entity, so it's not a number of different aquifers and aquitards and separate systems. that are uninterconnected. So anyway, I'm going to talk about, I'm going to very briefly over 3 slides talk about some of the field work we did. And then I'll go back onto some of the rock reactions and experimental studies we did in more detail. So part of the work we did, we looked at a lot of the different groundwaters in the area. So we were sampling from the Precipice Sandstone and the Hutton Sandstone around, this was kind of more of a regional research study. But so the injection, the proposed injection site was down here in West Wandoan. This was a tenement. As you can see, we didn't sample many other sites in those aquifers around this region, because funnily enough, most people aren't extracting water that deep, because we're getting very deep here and it gets expensive for people to drill their water bores so deep, so they're taking from the shallower aquifers. But we were sampling from some of the other regional areas. So some of the outcomes, I guess, that we had were that there was very long residence time, groundwaters around where the site was. It was quite old groundwater. So we looked at some different traces and cosmogenics, which would be favourable, I guess, because you're not getting groundwater movement, so you're probably not going to get migration. It was brackish groundwater, and we had elevated fluoride, which was above the levels for stock water and various use. But you could argue that, for example, there was a pig farm further down out here. And I think pigs, for example, you can give high fluoride because they don't have a long lifetime. Or you could perhaps use the water and mix it. Anyway, there was plenty of arguments in the media, but I won't go into that. We also found there were flow paths south and east, and we looked at a lot of different traces, but we also looked at things like the methane and CO2 that were present in the aquifers, some of the processes. So let's think if, for example, you did inject CO2 and you get a landholder who gets a gassy bore, you start getting people asking questions about whether you're leaking that or whether that's just natural. And we get that also around some of the coal seam gas regions. So I've looked at some of those where there's lots of people getting gassy bores, but then a lot of times this is natural gases that are present. And we found that with quite a lot of high variable concentrations of methane and gases in a lot of these aquifers. So I'm not sure how familiar people are with strontium isotopes, but they're one of the various different isotopes that we can use to look at different signatures. So strontium isotopes tend to be controlled somewhat by the recharge signatures, where the water's recharging, but also they interact with the rock formation that they're in. So they can end up with quite an, what's the word? Diagnostic signature in some cases. So this gives an example. So these ones in blue were for the Hutton Sandstone aquifer, and then in red we have the Precipice Sandstone reservoir, and you can see that we have, in most cases, we have quite different signatures. The Hutton Sandstone's more negative for various reasons I probably won't go into, but we could say, so the Hutton's less radiogenic, and we can say that, for example, this could support that we have disconnectivity between two of the aquifers. We did a multi-isotope study, so we did lots of different isotopes, which I won't discuss, to look at different signatures and, again, some of the cosmogenics, so we could look at residence times in the waters. And for example, we looked at stable signatures of methane and CO2 in a lot of the different aquifers. We could see that, so for example, in blue here, these are the Hutton Sandstone aquifer, and we saw a lot of high concentrations of methane and CO2, but we could look at these signatures and see that these were from what we call primary microbial CO2 reduction, forming methane, and that tells us that it's an in situ process, so we're getting microbial production of methane in the reservoir from the CO2. And then for the Precipice Sandstone, which is in red, we saw there had a mixed signature. So we had some microbial CO2 reduction to form methane, but we also have some contribution from thermogenic methane coming up from depth. And using different isotopes, again, we could look and see that it was consistent with where there's potentially been some historic migration of gases up from the Bowen Basin around some of those big faults. Some of the Mooney oil reservoir gases were thermogenic, which is not so surprising for an oil reservoir. But again, some microbial biodegradation. But I won't go into the groundwater work, but just to say that we did look at a lot of that, and it was quite an interesting area. But I'm going to talk more today about the rock reactivity. So, like I said, when we're injecting CO2, you're going to dissolve into formation water and lower the pH. And if we have some of these different impurity gases, then we can generate stronger acids. And various different minerals are going to be dissolving, so carbonate minerals, but also we're going to have silicate minerals which release ions, for example, magnesium, calcium and iron. And if we're releasing these cations from the silicates, then they can go on and react with the CO2 to form new carbonates, which is what we call mineral trapping. And that's considered like this most stable form of trapping. So that's favourable because you're making the CO2 a kind of a rock. There's other different kinds of trapping that you tend to get in the interim. But we also are going to end up, depending on your host rock, you can react with different minerals to release some different trace metals that you might not want released into your water, depending on the situation. So it's possible you can release various concentrations of lead or arsenic, for example. So you have some potential to change different properties in the water quality. There's also can be issues around corrosion of old well bores, depending on what your site is. These figures just show some micro CT images before and after. So we like to show the ones that you see some change, I guess. Although this is probably this will be a calcite cemented rock, so before and after. But the difference image is most obvious one. So you can see where the dark areas are formed, you're getting calcite dissolution to create some porosity in there. I think that was an evergreen formation. So with the reservoirs and seals, the reservoirs are Precipice Sandstone. It's a very quartz-rich sandstone, but we have trace amounts of some reactive minerals. As you're moving, so this is the lower Precipice Sandstone here on the log. As you're moving up, you go into the upper Precipice Sandstone where you have higher quantities of carbonates and other reactive minerals, feldspars. And then you overlying, we have the seal or cap rock, which is the evergreen formation. This is quite a lot of interbedded mudstones, sandstones, carbonate cemented rocks. And then underlying that, we have another seal. In this case, it's the Muliamber formation of the Bowen Basin. And I'll talk about that in a minute. Sorry. So this just shows some examples of QEM scan images of the lower precipice and the upper Precipice Sandstone. So kind of equivalent to the MLA work that is done in this centre as well. So like an SEM image that's had the different minerals allocated on there. So you can see on the left some of the lower Precipice Sandstone. Like I said, these yellow areas are the quartz grains, dark areas are intergranular porosity. And just some examples in the upper Precipice Sandstone, we're having smaller grain size and clay. A lot of the green areas are clay. This is just a few examples of many. It can be very diverse. And for pore throats, for example, the reservoir has generally large pore throats, but seals are very variable in different pore throat sizes. You have different organic matter in there as well. And these are some examples from the underlying Muliamba formation of the Barren Basin. So it's quite variable. So this is one of the clay-rich sandstones. Purple areas are siderites. So we have some siderite cements and interbedded coals, some siderite veins and different things that are going on. And if you look at some of the SEM images, we have so these white areas of the siderite cements, and then we've got some altered K-feldspar grains altering to kaolinite. So we probably have some natural weathering that's occurred in these previously. Yeah, here we have K-feldspar that's been naturally weathered into kaolinite. Anchorites precipitating around some of the pore throats. And these are some siderite veins, so it's possible anyway we've had some past natural hot fluid or CO2 circulation down there. But generally, so we characterise a lot of the reservoir and different seals, various different depths. We try and use a wide range of different depths and types of core with mineral characterisation. We also use, because in this case we were interested in the metal mobilisation, so we were looking at the metal content using total acid digests of core, some sequential extractions of the core, sort of using different fluids to look at were some of those metals loosely bound or in carbonates or silicates, for example. We also went to the synchrotron several times, which I'll mention briefly, to look at metals in specific minerals. And then we also did other characterizations. We used a reactor at UQ, which I'll talk about, to do supercritical CO2 water-rock reactions to look at the minerals. And then we used a lot of that data to go into geochemical modelling and different transport models. So just quickly with the synchrotron, we were going to have a look at different mineral hosts of some of the different metals in different core sections, thin sections. So we're doing high resolution scanning of various different elements. That's a picture of the synchrotron. This is just one example of many. So this is some from the Muliamba formation. Actually, the bedding plane's in this direction here, just to confuse everyone. So the side right here is in green. So this is what we call like a red, green, blue image. So calcium is in red, iron's in green, and in this case, potassium's in blue. So the siderites showing most of the hosts of iron. There's some apatite down here in between the coal layers. And we could see, so this is one of the synchrotron, but the concentration images. So we're going kind of yellows, the higher concentrations. So we're hosting arsenic in the pyrites and the coal. We also could see that lead was hosted in different minerals, but as well as in some of the sulfides, lead was hosted at low concentrations in the carbonates, so the siderites. And other elements like manganese are unsurprisingly in siderites. But also we're getting things like lead in some of those cements in some of the pores, and different zoned areas in some of these concentrations of things. But again, this sort of depended a little bit on different samples. So then we're doing CO2 water-rock reactions, where we're reacting different drill core sections from the different wells. So we're either using a pure supercritical CO2 or one with a mixture of gases to simulate what the industrial CO2 stream we expect. We were either using 12 MPa 60 degrees or 20 MPa 80 degrees, depending on which site and depth it was. And then we're sampling the waters during the reactions. So this is some examples. We're looking at sort of different iron concentrations over time and the reactions that were released. So unsurprisingly, the calcite cemented upper cores are releasing calcium, and siderite upper precipice ones are releasing iron in some different, so these are different depth sections. So often the released concentrations are varying with the rock core mineral content. Where we have cores from these upper reservoirs, we have a lot of carbonate mineral dissolution, so we're generating a higher pH, then we have less silicate mineral dissolution. But in the lower precipice, which is the reservoir, because this is very quartz rich, we tend to be generating a lower pH, it's not buffered. So we see in some cases some of the other elements releasing higher concentrations because of the acid content. So, for example, for lead and arsenic, so lead, we were getting some higher concentrations from some of the mudstone layers in some of those sandstones. Arsenic, this is just one example. We often tend to be releasing it before adding the CO2, and we could see from some of the sequential extractions it was often loosely bound in the rock, and then a lot of times precipitating or absorbing back out during the reactions. These are a couple of other examples. So again, you're seeing sometimes we're getting a spike of lead concentration and then tend to be precipitating or absorbing them back out. So in the case where we're using these gas mixtures where have oxygen in the stream, we often also ended up precipitating some iron oxides or iron hydroxy oxides, which are then kind of like a sponge bag for a lot of these elements. So you're sort of resequestering them back in. This is some examples from before and after SEM images. So you can see, for example, siderites reacting and corroding, releasing iron and some of the lead into the waters in the experiments. And these are some other examples before and after. So in this one, we've got some calcite cements dissolving after reaction. Some iron-rich chlorites tend to be leaching out iron and altering. When we have oxygen in the stream, again, we're getting some pyrites and often the sphalerite reacting. And if we have calcite cemented rocks, then we're dissolving out a lot of the calcite cements. And in a lot of the reactions, we're precipitating iron oxide type minerals where we've got O2 in the gas streams and NOx, which is oxidizing as well. And in some of the Mouliamba formation experiments, we're also precipitating various mixed carbonate minerals like ferroin carbonates, iron chromium oxides. So we're then resequestering some of those metals back in. So we take a lot of that different characterization from different experiments, and then we were with our collaborator in Canada, we were constructing special mineral scripts for doing some of the geochemical models. So the first step was trying to simulate at the experiment scale. So we were trying to do that to understand if we were to validate if we're using the right kind of reactive surface areas and using minerals with specific concentrations of metals to predict some of these other metal concentrations. Then subsequently kind of upscale these models and including absorption sort of processes in there. And then with mostly our collaborator was doing some reactive transport modeling. So we were doing this to look at different metals concentrations. So these images show some of the predicted plumes. So if you're getting CO2 injecting down here, this is kind of showing you just a cut off. So kind of half of the plume, if you like, from this axis. So the plume is moving out along some of the higher permeability layers and then sitting in this kind of area. over up to 100 years lifetime. And then this one shows us concentrations of lead in the reservoir as well, from 3 to 100 years. So again, released lead, but within the plume. So generally, in conclusion from those, we would get the metals released. Even though the concentrations were higher from the sulfides, the main hosts to release them were the carbonate minerals because they were, I guess, more reactive, with a minor contribution of them from the sulfides and chlorite minerals. And we had some mineral precipitation, but that's predicted more in the upper reservoir, where we have some of these more dirty reactive rocks. And then we provide sinks for some of these trace metals again, with absorption, especially when we got O2 co-injected, with precipitating out some of these iron oxide type minerals, which are absorbing and incorporating a lot of the metals. So I guess one of the takeaways was that there are water quality impacts, but they are restricted to the CO2 plume, which ended up going into the media as kind of research that was cited on both sides. So we were doing a lot of the research for the company, for CTS Go Glencore, but AgForce was also trying to claim that this was their evidence for what was going on. So anyway, there was a lot of things going on in the media. So in conclusion, reservoirs and cap rocks can have a range of reactivities to injected CO2. Depending on what your purpose of study is in this case, we tended to need a multi-pronged approach with different characterization. And I think I mentioned these in the last slide, but we did see mineral trapping and absorption in some of the dirtier rocks in the reservoir region in the seals. And some of these, and the methods are applicable to other storage areas, but of course outcomes are going to be different where you have, especially when you have different rock types, sort of basalts, carbonate reservoirs, for example. And we're still ongoing with some different work. So even though the risk of leakage out of the storage sites are very low, when you have a well-characterized and managed operation, sometimes the stakeholder perceived risk factor. There's a perceived risk factor, and if one of those ones, if it happened, then it would be a big no. So we're ongoing looking at what you're going to have occurring if some low concentrations of CO2 were to leak into some of these aquifers, with various experimental studies, and looking at some different isotopes that we might want to use to monitor, like strontium isotopes, in some of these aquifers in the Surat and in some of the wider Great Artesian Basin. So there's, I just need to acknowledge a lot of people for money and the synchrotron for giving us access, and some of the geochemistry labs in UQ, a lot of people from CTS Go Glencore who worked closely with us, and all of my co-authors from the beginning, because it was a big multiple effort. So thanks.
All right, thank you, Julie. We've got some time for questions, if there are any.
Hi, my name's Andrew. I have a question about the sort of scale and the upper limits of how much the system can absorb, in terms of, you know, if this ends up being something that industry users can use, can it absorb like a year's worth of a power station's output, for example? Like, what is the upper limits of what we're talking about?
It's a good question. I probably can't answer it very well, but Yeah, I probably wouldn't be able to give you a offhand number that made any sense. But I mean, in this case, they were looking at capturing all the CO2 stream from one coal-fired power plant and then trying to re-inject it. I mean, this was in the one I was talking about. It was a pilot scale study, so it was more. We'll do a small scale injection, so it was like 300,000 tons of CO2 a year for 3 years, and then you would do a pilot scale and then look if you could upscale that into something that's going to capture everything. So I guess between that site and the Mooney oil field, they were looking at using the captured CO2 from the power plant, but I probably can't tell you offhand without talking rubbish what what the actual numbers would be. And there are other sites. So in Iceland, they're taking a lot of the captured. They're taking all the captured CO2 stream, I believe, from the Hellished geothermal power plant and then re-injecting that in basalts over there at the moment. And they're also taking CO2 direct capture out of the air, which is a different kettle of fish, I guess, to re-inject that. So I guess that's a relatively new approach, because people are saying, well, if we've already overshot the amount of CO2 in the atmosphere, we kind of need to remove it. But then again, there's a energy balance, I guess, in doing that sort of thing. So sorry, I didn't really answer your question, but
Julie, I was wondering if you'd done any like geochemical modelling on what it might expect the results to be, say like using GeoChemist Workbench or Thermocalc or something like that to then compare what you're seeing once you look at these before and after reaction maps.
Yeah, so we were using GeoChemist Workbench. So we would tend to do these CO2-water-rock experiments, and then we're doing a wide range of different characterization, like with the metals and the different sequential extractions to try and pick where these metals are coming from. And then we were building like an experiment scale geochemical model to start with, to try and history match what we're seeing from the experiment with the model, and that helped us to build. So we were trying to build specific minerals. So you might want to build like a mineral that's siderite with X concentration of lead, arsenic, and copper, or something like that. That's kind of specific to that region or that reservoir. And then we were using that to also determine what the reactive surface areas are, which is one of the big kind of limit variables. And then going from that to incorporating adsorption processes, and then going from those, and with our collaborator, upscaling into a larger sort of scale reactive transport model. But it was it became quite complex because we were looking at quite a lot of different elements that were being released and absorbed. So at the end of the day, it's only a model, and I guess the purpose of wanting to do a pilot scale injection was to then see if you can see how that model then works in the real kind of field scale sense of the world. So yeah, unfortunately that didn't happen in the end, the pilot scale. So yeah, so yeah, so we could history match most of the experiments, but it was kind of one of those necessary steps, I guess, to have the experimental and the characterization, especially in this case, because a lot of the different minerals had different concentrations. Like when we were looking at it for that purpose of looking at the metal mobilisation, it could be very mineral specific, rather than just building a model and then making an assumption. So
I've got a question with respect to like I suppose the structural setting. The early slide showed that those holes were sort of basically in the syncline in the core, where you might expect there might be more structures like for migration. Has there been any work looking at possible structures and maybe look at the minerals in the structures? So if you did have migration, whether those structures could get just even clogged up and you wouldn't get that vertical migration, or just somehow doing some modelling to put structures in there?
Yeah, good question. So I probably didn't show any of the those kind of images, but mostly that on the company's side of things, they were doing a lot of the structural modelling. I guess looking at the geological structures, and then looking at the what's the right word, like the dynamic injection modelling. So the stuff that we were doing, which was the reactive transport modelling, it was based on that geological model, but that was part that was done mostly through CTSCo and Glencore. So they had various people who were working on that. So, like with regards to structures, like I guess if you mean if there's any large or small faults around the area and you have minerals in them. So there's, unfortunately, I guess, like a lot of the work was done, but there was, with seismic, there's an area around there where there was a lot of data lacking. So they were actually going out to do the seismic studies when the whole thing got shut down. So that's another, story. But there was going to be a lot of seismic work that was done, and then it basically just got shut down by the government. But there are some larger faults. So there's the Moonigunda-Windy fault that's fairly far away from the actual site or anywhere we predicted where the CO2 was going to go. But some of those faults, we did do some studies on some of those larger faults more regionally, and you could see that there were some areas where you're getting natural CO2, for example, or natural hot fluids that have migrated up there and then formed carbonates through a lot of the fault zones around there, or a lot of the patches. So again, I'm probably not quite answering your question, but half answering it. But so we do see in a lot of those areas, it was quite interesting because then you get a natural analogue, if you like, for what's occurring. So you're then, precipitating out a lot of carbonates, like calcite cements up in some of those faults and veins around that area, but not in the actual injection area itself where we're expecting. So.
So there's a question from Professor Salfam. What are we going to do if geologic storage loses favor due to perceived risk? If geologic CO2 storage loses favor due to the risk associated with it, the perceived risk associated with it, what will we do?
Well, I don't know, because at the moment in Queensland, unfortunately, this situation has meant that because this was kind of going to be the first project, because this one got shut down by the state government, and then the state government went on to do a big ban around the GAB. It's meant that now, I've heard that the government is looking at trying to investigate areas outside the Great Artesian Basin. I'm not sure if they'll reverse the ban or they'll try and modify it to look at, for example, because it went to the centre of the earth, so it meant we couldn't inject in any other areas like the Bowen Basin underneath. But because the government started off supporting the project quite strongly and putting a lot of support into it, and then there was a kind of a political backflip around the election time, and then a ban, I think it has unfortunately made quite a high, I guess the word sovereign risk maybe, for companies to come into the States if you wanted to do this sort of work. So I'm not really sure what that means going forward, like for different companies wanting to come into Queensland. I mean, around other areas in Australia, WA is very supportive of CCS. So there's various projects that are going on over there or in progress. And of course, in South Australia, Moomba's continuing, but it is very reliant on public perception and public acceptance. So if it becomes, if something happens, then we have a shutdown, then I think it will be a big problem, really. I mean, we don't have any other significant ways to remove carbon. Otherwise, I think it's meant to be part of the mix. I mean, it's not the one solution to anything, but it is meant to be part of the mix when we're using a lot of these different. We could continue using fossil fuels, and if we're going to have to extract carbon out of the atmosphere as well. I'm not sure if that actually answered the question. So.
Any more questions? All right, I think that'll be it for today. Thank you, Julie. Please join me to thank Julie. So next week there is no seminar because we are in the I think SMI has an all SMI day on that day. So and then there is also the semester break, but we've got some seminars lined up in the semester break as well. So the 11th of July we have Bill Haylock from PX4 Softwares, who will be talking on what are the mineral rights and authorities and how do they differ around the globe. So join us again on the 11th of July. Thank you.